Alright, so in this problem we have a capacitor is formed from two concentric spherical conducting shells. So we're not dealing with a parallel plate capacitor anymore. The inner shell has a radius of 10 centimeters and the outer shell has a radius of 15 centimeters. The potential between the plates of the capacitor is 50 volts. And by plates I mean concentric circles, or concentric conducting shells. What is the charge on one of the plates? What is the energy density essentially in between the plates, just outside of the inner shell? Alright, so in order to be able to calculate the charge, we need to know both the potential and the capacitance. We're given the potential in the problem, so that means we need to find the capacitance. So we have to have a way of calculating the capacitance of the capacitor. So when we did this for the parallel plate capacitor, we started with our potential difference equals the integral of E dot dl. So since these are spheres, remember starting with Gauss's law, integral of E dot dA is equal to Q enclosed over the electric constant. Since we're dealing with a sphere, we should probably put in a spherical Gaussian surface, which means that our area is going to be 4 pi r squared. This is why up here I plugged in charge divided by 4 pi r squared times the electric constant. And since we're dealing with circles, or spheres, those should be more centered. The electric field is going to come out. And remember our A and B, so A and B, we need to integrate along this path here. So this would be our dl. But in our electric field equation, that's actually dr. So this here should be a dr that we're integrating in terms of. Alright, so I'm taking the integral essentially of 1 over r squared, which gives me a negative sign out here, and then 1 over r, and I need to evaluate between rb and ra. And I've sucked the minus sign in, which is why this is a minus b rather than b minus a. I know my 50 volts, I know my electric constant, so I can plug that in. I know my two distances, so the 0.1 meters and the 0.15 meters. That allows me to calculate the charge as 1.67 times 10 to the minus 9 coulombs, or 1.67 nanocoulombs. Alright, so now that I find the charge, I can find the energy density at the 0.101 meter mark. Alright, so energy density is equal to 1/2 times the electric constant times the electric field strength squared. Luckily, I've already used Gauss's law to determine the electric field equation for a spherical distribution of charge. So I plugged in my Q divided by 4 pi r squared times the electric constant, and I found my charge, so the 1.67 times 10 to the minus 9 coulombs, divided by 4 pi times 0.101 squared. Now you do have to be careful here. Because this term is squared, this electric constant cancels out only one of these electric constants, so you still do need to divide by the electric constant. And that should give you 9.58 times 10 to the minus 6 joules per meter cubed.